Red-black trees are a complex type of balanced binary search tree, which have efficient find, insert, and remove implementations. Now, red-black trees are exactly what the C++ standard library uses in order to implement maps. But red-black trees are kind of complex. So before we discuss them, I want to first give you some backstory as to how they came about, so that you have a better intuition as to why some of the properties that red-black trees have are required. So their origin begins with 2,4 trees. These were introduced by German computer scientist Rudolf Bayer in the early 1970s. But this is a multi-way search tree where every internal node has k children and stores k-1 elements. So we have 2,4 trees that k can be anywhere between 2 and 4. So we have 4 nodes which have exactly 4 children, 3 nodes have exactly 3 children, 2 nodes have exactly 2 children. So those are the only type of internal nodes that we can have. And what makes this as a multi-way search tree is the fact that for our, let's say, 3 node, for example, this behaves really similarly to what we've seen with the binary search tree, except just that we have multiple branches, but there is an order defined for them. So everything in the leftmost subtree here, since we've got 3 children and we've got 2 elements here, everything in the left subtree is strictly less than 11. Everything in the middle subtree is between 11 and 24. And everything in the right subtree is greater than 24. You can expand this to 4 nodes as well, so anything in the left subtree here would be strictly less than 2. In this subtree would be between 2 and 6, and this one between 6 and 8, and this would be everything strictly greater than 8, but still less than 11. So most importantly, though, with 2,4 trees is that we satisfy this depth property. So all leaves have the same depth. In this case, they all have depth 2. So this is the height of our tree. And by satisfying this depth property, we can guarantee that the height of our tree is logarithmic, is big O log n. So this will allow for us to show that find, insert, and remove operations can be implemented in logarithmic time. But problematic with 2,4 trees is that we have these different types of nodes, 2 nodes, 3 nodes, and 4 nodes. So this can make an implementation complex. So later in the 1970s, Leonidas Kubias and Robert Sedgwick developed red-black trees in order to simplify the implementation by representing the 2, 3, and 4 nodes just by a single node type. So just a standard 2 node, so every internal node has exactly 2 children, but it has an additional color property, a color attribute. So every node is colored either red or black. Why red, black, and not purple, orange? This is, they say later that this was because the printer that they used in order to publish their paper, which introduced red-black trees, the best ink, which was clearest when they were done printing, was red ink and black ink. And then the other guy, Robert Sedgwick, had said that when they were kind of developing this and thinking about how to go about it, just in their offices, they had only black pens for writing and red pens for grading. So this is why we have red-black trees instead of some other colors. So the benefit of a red-black tree is that we'll end up getting the same logarithmic time performance, but we get a simpler implementation because rather than having different kinds of nodes to have to implement a 2, 3, and a 4 node separately and handle those cases separately, we'll have just one node type and then a color attribute for every node. So what exactly, just formally, is a red-black tree? So this is a binary search tree, so every internal node has exactly 2 children. A binary search tree where every node is colored either red or black, and we do so in such a way where we satisfy these 4 color properties. So just like with the other tree data structures we've seen, we're only storing the key element pairs at internal nodes, and we're not storing anything at external nodes. So we have 4 important color properties we have to satisfy. So we have to color each node red or black in such a way that we satisfy these 4 properties. One is that the root must be black. Every leaf, so every external node that we have, must also be black. And if we have a red node, so some internal node, which is red then, since all of our leaves are black, if we have a red node, then its children have to be black. So here we have a red node, both of its children are black. So any children of a red node are black. And then lastly, the depth property, which says that all leaves have the same black depth. So let's see here. Black depth is just, this is a little bit different than what you've seen with regular depth. The black depth of a node V, this is just the number of black nodes that you would have to travel through in order to get from that vertex to the root. So rather than counting up all vertices that you would travel through, including that one, we count up only those that are black. So for example, the black depth of this leaf is 3 because we go through 1, we're not counting this one, 2, 3 nodes, 3 black nodes in order to get from this leaf to the root. And the same as all of these others. So even though this one is at a different level, still we go through exactly 3 black nodes, this one, 6, and 9, in order to get to the root. So our depth property says that all leaves have the same black depth. So they might not be on the same level, but they at least have the same black. They travel through the same number of black nodes to get to the root. And since this is a binary search tree, again, we still have that same property that anything in the left subtree, this is less than whatever value is at our root, and everything in the right subtree, this is greater than whatever value is at the root. So we have kind of a better binary search tree at this point, a binary search tree plus some of these other extra color properties. And as it turns out, these color properties are very important in order for us to say that we can implement a binary search tree better as long as we have these. Okay, so we have a root property, root is black, external property, all leaves are black, internal property, children of a red node are black, and depth property, all leaves have to have the same black depth. So let's do a few examples to see yes or no, is this a red-black tree? So take a minute, go through these, and just try to check off, do you think this is a red-black tree or not? Does it satisfy those 4 properties? Let's evaluate the top left one first. So this one, this is a red-black tree. It satisfies that the root is black, all leaves are black, any red nodes we have, their children are black, and all leaves have the same black depth, which in this case is 2. So this one is good. The next one on the bottom is also a red-black tree. Root is black, all leaves are black. We have no red nodes to consider, so that's already true. And all leaves have the same black depth, which in this case is 3. Now the top right one, this is not a red-black tree. We violate that 2 properties. One, that the root has to be black, and then secondly, the internal property, which says if we have a red node, its children must be black. And then the last one, this also is not a red-black tree because we don't have that all leaves are black. Okay, one more example. Is this one a red-black tree? So again, hit pause, check to see, does this satisfy those 4 color properties? So this might look like a red-black tree initially. However, while we do satisfy that the root is black, all leaves are black, anytime we have a red node, its children are black, so this is good. We violate the last property, that all leaves have the same black depth. So here we have a node that has black depth of 2, whereas over here we have a node that has a black depth of 4 because it's going through 1, 2, 3, 4 black nodes. So this isn't a red-black tree. Now, satisfying those 4 color properties is important in order to show that the height of our red-black tree is bounded. So any red-black tree has a height big O of log n. So h, our height, is big O of log n. So provided we satisfy those color properties, we can say that this tree is balanced in that sense, that our height is bounded logarithmically. And why this is the case is dependent on those color properties. So if we take the longest possible path in our entire tree, so we've got our kind of large tree here, and we pick out of that the longest root to leaf path, so this is that path here on the right. So this is the height of our tree, h, longest root to leaf path. And we compare that to the shortest possible root to leaf path, and we call that the length of that shortest root to leaf path h star. So that means that the length of this path, h star, there is no other leaf in our tree which has a shorter path to the root. So if we take just this subtree, the one induced by if we take all of those nodes at a level no more than the depth of this node, then since we have no other closer internal nodes to our root, that means we have that this tree is completely filled with internal nodes at every level, right? Meaning that this part of our tree here, let's call it T star, the smaller portion of our tree, is a complete tree, a complete binary tree. And we know that for complete binary trees that their height is logarithmic. So that means that the length of this shortest root to leaf path, h star, is no more than log n. And how this compares to the longest root to leaf path, how much kind of larger this longer path could be, this is based on our color properties. So we know that the root is black, leaves are black, and then how is it possible that this path is actually longer if these external nodes must have the same black depth? Well, it could be that this path has less red nodes in it, and this path, which is longer, has more red nodes in it. But we know anytime we encounter a red node, its child must be black. So in the worst case, this longer root to leaf path is at most 2 times the length of this shorter root to leaf path. This 2 times happening if we exactly have that scenario where every other node is red. So we know that the length of this shorter path is log n, and we know that the length of this longer path is no more than 2 times this, so our total is 2 log n. So the height of any red-black tree is big O log n. This will be particularly important later when we talk about what the running time of algorithms are that work on a red-black tree. So we can always guarantee the height of a red-black tree is log n. If you have any questions, post on Piazza, reach out, let me know.